What's ready? Good day, viewers all over the world. You are welcome to Toidel online class. Today we'll be talking about the concept mapping. So I've actually introduced mapping, and we define mapping as a rule which assign an element, say element X in A, to a unique element Y in B. So where A and B are non-empty sets. That is, if you have two non-empty sets, say set A, and this is another non-empty set B. So if there is a rule that assign, let's say F, let's say we have element X in A, this relation will assign this element to get another element Y here. So that rule is called a mapping. And during our last class, we said we can have many elements because since it's non-empty set. So in a non-empty set, we have so many elements in that set, either set A or the codomain, which is set B. Set A is called the domain, where we have the initial elements. Then in this case now, let's say this are set Y will be f of x. That's the relation, or we can say that A is returns to B. This is F. So these are the, or we can say F such that A tends to B. This is how to write out a mapping. That is, this is a relation of a function. So it's taking element from A to B such that A to B, or we just say A. This is a relation to B, or function. This function acts on each element here to get the codomain. So all the elements in A is called domain, while B is called the codomain. Then in B, we can have so many elements. Let's say we have X, Y, we have Y, Z, M, N. Then here, let's say we have X, A, B. So it is possible to have something like this, as we have explained in the first class. So all the elements in A, which is the domain, is represented as X, A, and B. Then the elements in B, these are the elements in B. B is R, we have Y, Z, M, N. Okay, these are the elements in B. A is called the domain of this relation, of this mapping. B is called the codomain. But we have another element set, let's say R, which is equal to Y, Z, and N. If you look at all the elements in M, all the elements in B, this M, nothing is being mapped into this M. But when you consider Y, Z, and N, these are what something is being mapped into. So this is called the range of this mapping. So in this case now, the range is not a subset of B. So range is a subset of the codomain. But when we have one-to-one mapping, range and the codomain will always be equal, because in one-to-one mapping, everything has image. All the elements in A has image in B. So we have talked about the 5 types of mapping in the previous class. We talked about the first one, which is called the injective. That is one-to-one mapping. We discussed about that. That is in one-to-one mapping. It is one element to one element here. That is one-to-one mapping. That is when we have f of A. Let's say we have f of A. A is the element in the domain. We equal to f of B. Therefore, this implies that A equal to B. That is one-to-one mapping. It's one element to one element. Then if we have onto mapping, under onto mapping is otherwise known as surjective mapping. That simply means that the range of onto mapping is always equal to the codomain. The range of onto mapping is always equal to the codomain. So we discussed about onto mapping. In case of onto mapping, we can have two elements. We can have two elements at the domain being mapped into one element here. For instance, we can say 1, 2, 3, 4. We can get something like A, B, C. So 1 can be mapped to this. 4 can also be mapped to this. This is just an example though. This to this, then this to this. In this case now, you realize that two elements, 1 and 4, are being mapped into B. So this is an example of onto mapping. Then in onto mapping or one or surjective mapping, the range is always equal to the code domain. Let's say B is the code domain there, and this is A. And we are in the last class I've given us the condition for us to have a mapping. All the elements here must have an image in the code domain. Then one element here can have two images here, but it's not possible to have two images assigned to one element. So I gave all the conditions there. We also talk about bijective. Bijective is when a mapping is both one-to-one and onto. So we gave example, and we talk about identity mapping. Identity mapping is when we have the value of the domain element in the domain is the same thing as value of the element at the code domain. Then we also talk about constant mapping. Under constant mapping, all the elements in the domain has just one image at the code domain. All the elements in the domain will have just one image at the code domain, and that is constant mapping. So I gave example on each of the mapping in the last class. So today I'll just give one example, then I'll move to composite mapping. Example, let's say example one, still under mapping. We say let F such that this is a set of real numbers is taking elements. So this mapping now, we can refer to it as a function because we are actually dealing with numbers. Be a mapping from set of real numbers into another set of real numbers given by this mapping is given by f of x is equal to 3x plus 5. So the question now says we should show that f is bijection. That is, we should show that f is both onto. You know, I said the third type of mapping that we have is bijective mapping. Bijective in the sense that mapping is both onto, it's both one-to-one and onto. That is both injective and surjective. Another word for one-to-one mapping is injective. So another word for onto mapping is surjective. So when we have a mapping that is both onto and one-to-one, it's called bijective. So that's what we want to show now. So in this case now, the first thing that we're going to do is that we show injection. That is, we want to show that mapping is one-to-one. So how do we show that? Under one-to-one mapping, f of A is always equal to f of B. F of A is always equal to f of B. That is, each element will have a unique image in the code domain. Each element will have a unique image at the code domain, and that is the uniqueness of one-to-one mapping. So f of A is always equal to f of B. So if you apply that here, you know, when we have f of x in the question, it is 3a. So f of A will be 3a plus 5 being equal to 3b plus 5. Then of course 5 we can subtract 5 from both sides so that we have 3a to be equal to 3b. Then 3 can divide both sides so that we have a equal to b. Since a equal to b, it shows that f is injective. F is injective. That is, f is injective. F is one-to-one. That is one of the conditions that makes this mapping to be bijection. It must be both injection and surjection. So that is the first condition. Then the second condition that we're going to check before we can conclude that the mapping is, the second condition that we check is surjection. That is, we want to show that the mapping is onto. And if we want to do that, we just say for all y that belongs to set of real numbers, there must exist a that belongs to R, such that f of a, our f of a must be equal to y. And that's the condition. That is the condition in this case now. That is, on that onto, this is the condition. Our f of a must be equal to y. That is, when we apply that function, that mapping on each element of a, we must have an image in the code domain, and the code domain must be equal to the range, and that is the condition here. So this implies what we have here now implies that implies that our f of implies that 3 f of a will be 3a plus 5 can be equal to y. Then we can make a the separated formula. 3a can be equal to y minus 5. Then a is equal to y minus 5 all over 3. And in this case now, this our image, this a that we have now is fractional. But since we are in the set of real numbers, so we are on the safer side, irrespective of what we have. This one implies that f is subjective. So f is subjective, is subjective. So that is the condition. So since we have shown that f is both one-to-one and onto, that is injective and subjective, therefore f is a bijection. F is a bijection. If we're able to show the two conditions, that f is both one-to-one and onto, please, we need to go through the first lecture on mapping before this mapping 2, for us to have proper understanding on how a mapping can be both injective and subjective. So we have done we have defined everything, all the types of mapping in the first lecture. So the first lecture is actually important for us we just want to build on what we have discussed in the first lecture. So it is important to go through the first lecture. So today we'll be talking about composite mapping. Composite mapping. This composite mapping. So under composite mapping, let's f, we have a relation or a mapping that takes element from x to y. This is one relation or one mapping. And we also have another one, G, that now takes element from y to z. Look at, in this case now, x is the domain, y is the codomain. In this relation, in this mapping f, the way we now have another mapping, G, y, which happens to be the codomain under f, is now the domain under G. Then z is the codomain under G. So if this is what we have, so if we let this be two mapping, let this be two mappings, that is f and G are mapping such that, in this case now, be two mapping such that f is the domain of G. F such that the codomain of f, this is the codomain of f, y is the domain of G. Then the mapping takes an element from x. Now this mapping is possible for this mapping to takes an element from x to produce in y. That's the first thing, via z. So it is, in this case now, it is possible for the mapping now to take an element from x here directly to z via y. That's what we are trying to say under composite mapping. X is the domain under f, y is the codomain under f. But this y that is the codomain under y is now the domain under G, under this mapping or relation G. So which is taking element from y now to z, which is the codomain. We are now saying that it is possible to move directly from x to z via y, and that is the meaning of composite mapping. So what we are trying to say here is that we can move directly from x to z via y. Then if that is what we want to do, then we denote it as G of f. That is, we can move directly, or which is otherwise known as GF. In some textbook, just is GF. Under composite mapping now, f is one mapping, is one relation, G is another relation. X is the domain of f, y is the codomain of f. Under G, y, which happens to be the codomain of f, is now the domain of G. Then we now have the codomain z. So we are now saying that it is possible to move directly from x to z via y. Then this is what, if you want to do that, then we make use of this concept, G of f, that is from G to f. So we now start from f now. We define the relation when f under f. Once we get the result, we now use this relation G on f. Then we'll be able to come out with something reasonable. Let me just draw. Let's have a diagram that will help us to explain that concept better. Let's say we have, this is x, this is x. We have elements in x. Let's say P, Q, R, S. These are the elements. Then in this case now, let's say this is y. We have elements, say A, B, C, D. Then we now have another non-empty set Z. So this is X, Y, Z. That's what we have. So in this case now, this element, let's say P, this element to A, we have Q to C. Notice the mapping. We have X to B. Then probably we have R to D. Then in this case also, we have C to X. We have D to Y. Then we have B to Z. Then probably, then we also have A to X. In this case now, this first one, the relation here is F, and the relation here from Y to Z is G. So that's what we have. So it simply means that the mapping F takes an element from X to Y and produce the image in Z. This mapping F now takes an element from X to Y, and this Y now, it takes an element from X, takes an element in X and produce the image in Y. It produces the image here in Y. Why the mapping G takes an element from Y and produces the image in Z. So how do we now write that? For instance, this first one now, we say G of F, that is P. If F acts on P, we are able to get A. That is what we are going to have. That is, if F, this relation mapping acts on P, F of P will produce A. Okay? This element, this is the domain of this is the codomain of F. Then under G now, this is the domain and this is the codomain. So if F acts on P, we get A. Okay? Then we now go ahead and say G. If G now acts on A, what are we going to get? We are going to get X. So this is a typical example of a composite mapping. There are two relations here, F and G. So this F, if it acts on the element under this domain, we are going to produce codomain here, the image here. So if another function or another relation G now acts on A, what will be the image? X, and that's what we get. So there are two relations or two mapping involved here. Let's talk about this X. When we have G of F of X, in this case now, if F acts on X, what will be the image? It will be B. Okay. Then if G now acts on B, what will be the image in Z? It will be Z. Okay. This is how to combine two relations or two mapping together. So the first one, we allow the first one to first act, then we go ahead and use the second one. So the mapping, this mapping now, the mapping G of F is called, this mapping is called a composite. It's called a composite mapping. So the mapping G of F is called a composite mapping. And in some textbook, we only have something like GF. That's what you are going to have. Is that you have it like this, or they just write GF. So this is talking about different two relations acting on three non-empty sets. And that is what we are going to have. So I'm going to take example now in order to buttress our points on composite mapping. Let's just take one or two examples, then we go to inverse mapping. In this case now, let's say example, let's say example one. We have let the mapping F and G on R on the set of real numbers be defined by F of X is equal to 2X minus 3 and G of X to be equal to X plus 1. So the question now says find G. The question says Roman figure 1, find GF. Then Roman figure 2, find FG. That is G of F and F of G. So that's what we want to find. So look at this question now. There are two functions or relation involved. f of x equal to 2x minus 3, and g of x is defined as x plus 1. So g is acting on, what is f of x? Is acting on 2x minus 3. Okay, so then g, if you look at g, what is g? G of x is x plus 1. So g of 2x minus 3 will be 2. G of 2x minus 3, g of 2x minus 3 will be 2x. G of 2x minus 3 will now be 2x. Let's look at it very well. No, this is let's say this is square. There's square on this. There's square on this. Sorry. There is square on this. 2x squared. That's what we have. So in this case now, we are going to have this to be 2x squared. 2x squared minus 3. So f of x is defined as 2x squared minus 3. So g of f of x, just write out f of x. Then what is g of x? G of x is x plus 1 that we are looking for. Then that's Roman figure 1. Then if you want to do the second one now, the second one where we have fg, that is f of g, we are going to have f acting on g of x. In this case now we have f. What is g of x? X plus 1. G of x is x plus 1. Then what is f? F of x is 2x squared minus 3. So f of x plus 1 will now be 2 into brackets x plus 1 squared minus 3. That's what we are going to have. Then if we express that further, we are going to have 2 into bracket x squared plus 2x plus 1 minus 3. Then if we expand, we are going to have 2x squared plus 4x squared plus 4x plus 2 minus 3. Finally, fg will now be equal to 2x squared plus 4x minus 1. And that is what we are going to get. So what can we deduce from here? We realize that g of f is not equal to f of g at all time. So please, we should note that it is possible in some cases, but it's not equal in general. And that has to do with commutative, this commutative property. When we discuss binary operation, we talk about commutative property. So we should note that the operation of composition of two mappings is not commutative in general. So in this case now, we can talk about commutativity property here, g of f. If this is commutative, it simply means that g of f must be equal to f of g. But in general, the composition of two mapping is not commutative in general. Of course, in some cases we can have it, but in most cases it is not. So we cannot generalize. So we take one more example. So in this case now we are given, let GF, G, and H. Here we have three relations or mapping, be mappings on the set of real numbers defined, and that mapping is defined by f of x is given as 2x plus 1. The question now says show that f of g into bracket of H is equal to F of into bracket G of H. That is, this one now is talking about associativity. If you have gone through binary operation, we have discussed binary operation. So what we are trying to say, in essence, is that we want to look at if you have FG into bracket H, are we going to get the same thing as you saying first taking F, then G, H? That's what we want to check. So if you are able to establish this fact, it simply means that the composition, it simply means that the operation of composition of two or more mappings is associative. If you're able to get the same answer, then we can generalize. But we know that when it comes to commutative property, it does not hold under the composition of two mappings. So let's try this out, where we have F of G into brackets of H. Then what do we get here? In this case now, it's same thing as use. It's same thing as saying FG. FG, then this same thing as saying FG. We first want to take H. We first want to establish the fact. We say FG. Then what is H? H is defined as what? 3x plus 2. That's what we get. Then this same thing as F. What is the definition of G? G is defined as x. When you have G of x, is defined as x squared minus 3. So if you now have Fg of this is going to give us 3x plus 2. Look at it, 3x plus 2 squared minus 3. That's what we are going to get. H, of course, when we have H, we just write it out, 3x plus 2. That is H. Then when we now relate G on H, we are going to have G of x is x squared minus 3. So G of 3x plus 2 will be 3x plus 2 all squared minus 3. Then we can, if we expand that, we are going to have x squared plus 12x. That's what we are going to get. Then what is F? F is defined as 2x. F of x is defined as 2x plus 1. So F of everything here will be defined as 2 into bracket 9x squared plus 12x plus 1, which represents x here, then plus 1. So if you now write out everything, we are going to have 18 x squared plus 24x plus 2 times 1, 2, 3. So F of G of H is given as what we have on the board. Then let's go ahead and do the other side. If we are able to get the same thing, then we can go ahead and generalize. When we now have F of then G of H. So what do we do here? So we are going to start from what is F of X? F of X is given as 2x plus 1. Then F of this will now give us, this will give us 2 into bracket G of H plus 1. That's what we are going to get. That's what we are going to get. Then this same thing as you saying 2 into bracket G H of X plus 1. Then this is the same thing as 2 into bracket G. What is H of X? H of X is given as 3x plus 2. Okay, plus 1. Then from there, we know G of X. G of X to be x squared minus 3. So we are going to have 2 into bracket 3x plus 2 all squared. G of x is x squared minus 3, then plus 1. This is what we are going to have. Then from here, we have 2 into bracket. When I expand this, I'm going to get 9x squared plus 6x plus 4 minus 1 plus 1. At the end of the day, I'm going to have 2 into bracket 9x squared plus, no, this 12x. This will be 12x plus 12x plus 3 plus 1. Then I can go ahead. This is 3. Here will be 1. So when I expand further, I'm going to get this to be equal to 18x squared plus 24x, then plus 3. So from there now, we have been able to show that F of G, we have been able to show that F of G of H is equal to F of then G of H. So we have been able to show from what we have done now, we have been able to show that this is equal to this. Then in general, we can say that the operation of composition of two mappings is associative in G. So the operation of composition of two or more mappings is associative. So we can generalize the composition of two or more of the composition, the operation of composition of two or more mappings is associative in general, since we are able to show this. So that is that about composite mapping. Then I will go ahead and introduce inverse mapping. Of course, inverse mapping is straightforward and very simple. So under inverse mapping, of course, we are all familiar with inverse. For multiplication now, if you have x, the inverse of this will be 1 over x, which same thing as s inverse. So we are all familiar with inverse. If it's addition, if this is x, then the inverse of this will be minus x. So the word inverse is something that we are all familiar with. Then if you now relate this to function or mapping. So if you have a mapping f defined as taking element from A to B, if this is a mapping f, or we can write it as say A takes element to B f, if this is the mapping. So we all know that f of A, that is A is an element here, is going to give us B. That is a known fact. That is, if this relation, this mapping takes element from A to B, once this mapping operates on each and this is a non-empty set. This is also non-empty set. If this mapping F operates on each of on every element of A, let's say A, we are going to get the image in B, which is small letter, because we normally represent the element of a set with small letter, but that set with capital letter. So this is what we know. If F takes element from A to B, automatically we are going to get this. We know this. This is what you know. Then, if you now denote the inverse of F as F inverse, then the reverse will be the case. F inverse will now be B to A. Under F is A to B. If you now want to take the inverse of this, automatically it's going to take elements from B back to A. The reverse will be the case. We understand? Then what will now happen here? We are going to have, if F of A is equal to B, then we now know that F inverse of B must give us A, vice versa. F is a mapping taking element from A to B. Then we now write F of A is equal to B. So if you now want to find the inverse of that mapping, F inverse, that means that the reverse will be the case. It's going to take element from B now back to A. Then if we take the inverse of F inverse of B, we must get A. And that is the condition. So we should note that F inverse, that is the inverse of this map of a mapping, is defined only when F is 1-to-1 and onto. That is, we can only talk about inverse of a mapping when that mapping is bijective. When it is bijective, simply means it's 1-to-1. Then under 1-to-1 is when you have one element to one element in the domain to codomain. Then onto simply means that the range is equal to the codomain. So the two conditions must be satisfied before we can talk about inverse mapping. Then F and G. Then when we now have composite mapping, we should note that F and G are both onto and 1-to-1. That is, G of F is also onto and 1-to-1. That is, if we have G of F all inverse, is same thing as F inverse G inverse. So let's just take note of that also. So we should take note of that for us to be able to have inverse mapping, that mapping must be bijective. It must be both onto and 1-to-1. So let's just take example to buttress our point. Let's say example 3. Example 3, the question says the function f over the set over the set of real numbers, say set R, let me just abbreviate, over the set of real number is defined by f of x is equal to 1 all over 2x minus 3. So the question now says find f inverse of x. Solution. This is the function. The function is also a mapping. When the codomain is a set of numbers, so we call a function a mapping. A function is also a mapping. When the set of the codomain is a number, so a function is a mapping. So we can just let, in this case, we can let y equal to f of x, and it's equal to 1 all over 2x minus 3. That's what we get. Of course, I want to replace f of x with y now, so that I'll be able to write the inverse. So you permit me to do that. So instead of f of x now, I'll be using y. So I've now said y. This 3 can come here. By the time minus 3 crosses this equality sign, I'm going to have it to be plus 3 here, equal to 1 all over 2x. Then I can cross multiply to have 2 into bracket y plus 3 to be equal to x. Okay. So in this case now, my x is given as 2 into bracket y plus 3. Then of course, x. So in this case now, x is same thing as if y is a function of x. If y is a function of x will now be the inverse function of y. If y is a function of x, then x will be inverse function of y. That is the implication. So my x here now, x here, I can write x as the inverse function of y. X can be written as inverse function of y, so that it will be 2 into bracket y plus 3. That's what I'm going to get. But if I now want to perfect everything now, I can replace x. Since I have x here, I will replace y, wherever I have y here, as x, so that I can have f inverse of x to be equal to, I can replace that, so that I can have f inverse of x to be equal to 2 into bracket x plus 3. And that will be the answer. Look at the function f of x is defined as this. We want to find f prime of f inverse of y x. So I define y as my f of x, and it's given as this. So instead of f of x now, I change everything to y, so that I have y plus 3 to be equal to half x. When I cross multiply, I have 2 into y plus 3 to be equal to x. Then what is x? X, if y is a function of x is f inverse of y. Then I decide to write it in this form. But since this is x, I decide to replace, wherever I see y here, I replace it with x, so that I'll be able to write out the inverse function of f of x, and that is what is given. It's given as what we have on the board. So we can take another example. Say example 4. Let's take another example before we call it a day. So in this case now, for us to have proper understanding about this topic, mapping, about this mapping 2, we must go through the first teaching on mapping. We just have to go through the first teaching before we'll be able to have proper understanding about this concept. So please, let's try and do that. Let's try and go through that. So let's say example, f is defined as f such that x tends to 3x minus 2. This is the domain of x. Then the codomain, this is what you get. And g such that x plus 1 are two functions as two functions defined on set of real numbers. The question now says show that fg of x all inverse is equal to g inverse into bracket f inverse of x. That's what we want to show. We want to show the inverse of that composite mapping. So what do we do here? What are we expected to get here? So we go over this briefly, then we can close the class. solution. So in this case now, what do we do? That's what we want to show. So how do we show this? We are going to start from f of x, solution. So f of x is defined as what? F of x is defined as f of x is defined as 3x minus 2. That's the definition. That's the definition of f of x. From the question, that is x, and that's the definition of f of x. Okay. So what do we do here? We can say let y is equal to f of x and it's equal to 3x minus 2. Okay. So that y plus 2 can be equal to 3x. We want to make x is subject of formula. Then x can be equal to y plus 2 all over 3. That's what we get. So we can get that. Then what is x? X, of course, we all know that x is the f inverse of y. So in this case now, our x, which is equal to x is same thing as f inverse of y, is given as y plus 2 all over 3. So now we can start to write everything in form of x, so that I'm going to have f inverse of x to be equal to x plus 2 all over 3. And that's what we have gotten. Okay, that is what we are going to get under f inverse of x. Then what is g of x? We are able to show that we have gotten this. F inverse of x is this. So what is g of x? What is g of x? So we go ahead and find, we have gotten the f inverse of x as x plus 2 all over 3. Then we know that g of x is equal to x plus 1. Then we can represent this. We can say let z represent g of x is equal to x plus 1, so that we can find everything in form of x. Then z minus 1 is equal to x. So x is equal to z minus 1. Then x, at the same time, x is going to give us z inverse. Here now, x will now give us g inverse of z, which is equal to z minus 1. Let's represent everything as x, so that g inverse, therefore g inverse of x will now give us x minus 1. That's what we are going to get. Then now let's go back to the question. G inverse of f inverse of x, that's what we want to find. So in this case now, we have g inverse of, what is x inverse? X inverse, f inverse of x is x plus 2 all over 3. That's what we get. Then what is g inverse? G inverse simply means z, x minus 1. If that is the case, then I will just have x plus 2 all over 3 minus 1. That is what we are going to get. Then if I find the LCM, if I try to rewrite that, if I find the LCM here, I'm going to get, if I find the LCM, I'm going to get LCM here is 3. I'm going to have 3. So that will be x. I'm going to have x minus 2. If I find the LCM, I'm going to have, so from there now, if I find the LCM, I'm going to have x minus x plus 2, then minus 3. Then at the end of the day, I'm going to have x minus 1 all over 3. So that is what I'm going to get. So it shows that my g inverse into bracket f inverse of x is given as x minus 1 all over 3. So we have gotten the value of the one side of the question. So let's do the second side and see if we are going to get the same value. So if we're able to get the same value, then we can generalize. So that's what we have. So what is the second part? We want to show that, okay, f of g of x raised to power minus 1. So in this case now, we want to find f g of x. This is what we want to find here now. So how do we get that? That's what I'm about to do now. So how do we get that? Let's just, so let's go ahead and solve that. So how do I get that? So let's just concentrate and get that. So I want to go ahead and find f g of x. So we want to find f g of x, everything inverse. Before I can find everything inverse, let me first find f g of x. So if that is the case, then I'm going to have f. What is g of x? G of x is x plus 1. Then what is f? What is f? F of x is defined as 3x minus 2. So I'm going to have 3 into bracket x plus 1 minus 2. Then I'm going to have 3x plus 1. That's what I'm going to get. So this is the whole of this. How do I find the inverse of this? So I can just say, let P represent everything here. 3x plus 1. Excuse me. So that P minus 1 can be equal to 3x. Then I want to make x subject to formula. So x invariably will be P minus 1 all over 3. That's what I'm going to get there. Then what is P? P is the same thing as f of g of x. So in this case now, x will not be the inverse. So x will be the inverse. So I will now say, therefore, x, I can try to represent this x, which is the inverse. X, which is the inverse of x, is given as f g of x inverse, f g of x inverse is equal to, this is f g of x inverse is equal to, no, this is p. P of x inverse is equal to p minus 1 all over 3. Then f g of x inverse simply means just change p to x. Then we are going to have x minus 1 all over 3. That's what we are going to get. Look at f of g of x. I try to represent it as p is equal to this. When I make s the substitute of the formula, I'm talking about the inverse of this. Just like when we said if y is equal to f of x, then x will be what? F inverse of y. This has been the standard. So if f of g of x is equal to this, if I make s the formula, s will be inverse of what we are given. Though I decide to represent everything as p, so that in this case now I've gotten the inverse here. So fg inverse of p is going to give us this. So I'll just substitute wherever I see p, I substitute it as x. Then f inverse of this. Therefore, we have been able to show that f of g of x inverse is equal to g inverse into bracket f inverse of x. And that is what we are asked to show. So I would love to stop the class because of our time. If you have further questions on mapping, just write it at the comment section. I promise to attend to it. Thank you for your time, and God bless you all.